Okay, so last class we wrapped up the transient analysis part, chapter 4, and we're starting the chapter 5, which is a steady state sinusoidal analysis. So, the last chapter, in the transient analysis, we sort of introduced the idea of, okay, the decay of a waveform or rise and fall times of waveforms across voltages and across capacitors and through inductors, etc., right? So, we saw that there is a time varying nature related to any time you have a capacitor and an inductor. But the sources that we used were typically DC, right? So we typically use DC sources only. And the rise of the current or the rise of the capacitor voltage or the decay in the inductor current, all of these were happening in a few time constants, right? It was a few time constants, and then the effect would go to zero, right? You would charge the capacitor, and then there was no more current would flow. You would create a flux around the inductor and store the energy there, and then the inductor would be like a short circuit, right? So it's there's after that nothing changes. I mean, it's a simple put the inductor short circuit, put the capacitor open circuit, and solve the circuit, right? And you were able to get sort of a steady state response for the solution, and then the transient response. You drew some of these waveforms, and you saw the effect of charging capacitor, discharging capacitor, charging inductor, discharging an inductor. You saw that in these circuits, yeah. Here we're talking more about a sustained time varying waveform, right? So here you would expect that with a resistor there's nothing changed, nothing different. Anytime you have a voltage, you have a current. The relationship between them is V equals IR, right? But with a capacitor and an inductor, you would expect something more to happen, right? Because of these capacitors and inductors are storing energy, and they are basically, with inductors, they are delaying the rise of current, or they're delaying the change of current. With a capacitor, it is delaying the change of voltage, right? So now you have a time-varying signal that is sinusoidal in nature. So you would expect that if you apply a sinusoidal voltage across an inductor, what would the current look like? Well, again, V equals LdI by dt, right? If the voltage is sinusoidal, the current is what? The integration of the voltage, right? V equals LdI by dt. So I is equal to 1 over L integral of V dt, right? So it's the integral of the voltage. So if this is sinusoidal, the other will be sinusoidal as well, but phase shifted with, so this is sine, this is a cosine, this is a cosine, this will be a sine. They will be shifted with respect to each other by 90 degrees. In an inductor, current will lag by 90 degrees because inductors are delaying the change of current, right? So current will lag the voltage by 90 degrees. So if the voltage is a sine, you would expect to see the current to be a sine with a phase shift of 90 degrees or a minus cosine in that case, right? So, and same thing with capacitor. Capacitor, IC equals C dVc by dt. So if you have a sinusoidal current or sinusoidal voltage applied across the capacitor, the current is the differentiation of this voltage. The written sine is a cosine. So what's going to happen is that if you have a sinusoidal voltage, the current is actually a cosine that is leading the voltage by 90 degrees, right? So, and then you can have a combination. You can have an RL combination. The combination can either look like an RL or it can look like an RC. It can be a combination of R's and L's and C's, but we can find an equivalent to them that is either going to be RL or RC. The equivalent cannot be RL and C. But the equivalent will either be RL or RC, right? So if the equivalent is RL, then the current will be lagging the voltage, right? As we said, lagging the voltage instead of by 90 degrees, by something a little less than 90 degrees, depending on how much resistance. If we have if it's purely resistive, then voltage and current are in phase. You put voltage, you get current that's exactly the same shape, but scaled down by magnitude only, right? But if it's purely inductive, the current runs after the voltage, right? It's 90 degrees lagging, right? So if it's RL, if it's a combination of R's and L's, it's between the 0 and 90 degrees. It's between being in phase and being 90 degrees lagging the voltage. And if it's RC, the current will be if it's pure C, then the current leads the voltage by 90 degrees. And if it's an RC circuit, RC equivalent impedance in this case, then it's going to be, instead of leading by 90 degrees or being in phase, it's going to be somewhere in the middle. It's going to lead by some degrees, that is between 0 and 90. Right? So this is sort of what we're going to talk about in this chapter. So obviously now we bring in this phase concept into consideration, right? Before, when we were solving circuits, we were talking about, anytime you have a voltage magnitude difference between nodes, then current will flow. But now it's very different, because now I can have the same voltage at two nodes, but they can have different phase. Right? So if they have different phase, will current flow or not? It will flow, because forget about them being AC quantities, right? Think of them as instantaneous values. Instantaneous values, if you have two voltages that are not in phase, it means that instantaneously they are different. If instantaneously they're different, then instantaneously there is a current between the two nodes, right? So think of any AC quantity as at any time it's a pure DC. Then at some point, at any point in time, there is a difference between the quantities, even though they're RMS phasor. They're phasor. You've studied phasors before or not? Sinusoidal signals, you can represent them in phasor form, right? Yes, no? We will study it anyway, but have you not been exposed to the concept of a phasor quantity before? In what context? In your chemical engineering? You have not. But in math or physics, right? Physics, you've taken some professor in physics, what? Okay, so we'll talk more about that. We don't need you to know it. I don't depend on that the fact that you know it, but we will discuss it. But basically, if you have two time domain signals, two sine waves, but one starts at t equals 0 and one starts a few seconds later, right? Then in the time domain, they are phase shifted with respect to each other. But let's say they have the same peak magnitude. If they have the same peak magnitude and they have exactly the same shape, then if they flow through a resistor, then they will dissipate the same amount of power in this resistor, right? But what is the difference between the waveform? The difference between them is the phase shift is different. So how do you represent that? We represent that on the complex plane, a real and imaginary plane, somehow. And we'll talk about that in the class. So yeah, that's really the summary of what we're going to talk about in this chapter. How do you take these AC quantities, represent them as phasors, and then after you represent them as phasors, now they have magnitudes and angles. Why do we care about these things having magnitudes and angles? Because, as we said, now when we talk about AC quantities that have magnitudes and angles, you may have a circuit with two nodes that have the same voltage magnitude. From our previous discussions, no current will flow. But because we are talking about AC quantities that have magnitudes and angles, instantaneously there is a difference. So instantaneously there will be current flowing between them. So because of the angle difference. And this is actually how our power system functions. Right? Our power system functions this way. If you measure the voltage in the sockets, in the electrical sockets that we have in this room versus the sockets you have at home, will the voltage magnitude be the same or not? Or should it be the same or not? Should it be the same or not? What is the voltage that you measure between in your outlets here? What voltage do you expect to see? How much? Yeah, 230, 240 volts. It's not fixed value, but it's something it's a number that changes. But typically it's around 240 in Qatar. It's around 240 volts, and what we call RMS. RMS is a sort of another quantification of the energy in the signal. And we'll talk about RMS later. So it's a 240 volts. And you expect to see 240 volts here, you expect 240 volts in your house, 240 volts everywhere. So all of these are different nodes in the circuit, right? At the end of the day, our power system looks like a big circuit. Our power system looks like a big generator here, and then this is one house, another house, another house, another house. Basically, that's what this really is. And theoretically, we should be all getting the same voltage across each other. I mean, across the terminals that we see at home, for example. It's not that simplistic because here I did not put an impedance, but all of these are cables, right? These cables have voltage drops or have resistors. These resistances and inductances, we will see now, inductances also come into play, but let's say they're all resistors. If it's an inductor, it will be a short circuit, right? For a state, if this was DC, right? If it's not DC, we will see why it will have a voltage drop across it. But if we have these voltage drops, that means the person staying furthest away from the generator is seeing the lowest voltage, right? That's not fair for his equipment, because if his equipment is consuming a certain amount of power, power is equal to V times I. What does that mean? It means that his current will be higher than everybody else's, right? So that's not allowed, of course, right? So we want to make sure that everybody's voltage is similar. So what we have around the power system is these transformers that allow us to regulate the voltages in different places. So we can raise the transformer, raise the voltages and lower the voltages so that we can suit. We also have other devices in AC systems. We will see that if you have equivalent RL, this is an equivalent RL circuit that's representing your house, right? We will see that if I counter the effect of the L by putting a capacitor. Capacitors are in AC systems. Yeah, I have a good analogy, very nice analogy. Okay, so in AC systems, capacitors and inductors are like, if you're these bikes with multiple people that can be on the same bike. So the objective is to have the bike move forward, right? So the power that everybody's sitting and cycling, generating power to move the bicycle forward. Somebody throws a ball at the people on the bicycle. What's going to happen? What? No, we don't want to stop. We still want to satisfy the load. We want to keep going forward. So some people will do this to duck away from the ball, right? How about other people? Is everybody going to go to one side? Probably some people go this way. I mean, if we don't want the bike to fall, okay? Then some people will go like this, and other people will go in the other direction, right? And that's what inductors and capacitors do in a power system. Right, so they store energy sort of in different cycles, right? And we will see you remember I said that the capacitor current leads the voltage by 90 degrees, and the inductor current lags the voltage by 90 degrees. So if we draw a voltage waveform and draw two current waveforms, one leading by 90 degrees and one lagging by 90 degrees, and then draw power V times I in both cases, you will see that the power flowing through the capacitor versus power flowing through the inductor are complementary. When one is positive, one is negative. When one is positive, one is negative. Right? So what these two are doing is then complementing each other. So if a system looks more like an RL circuit, I want to sort of counter the effect of this inductance causing some voltage drops around the system. What I can do is I can put some capacitance, right? So which would make the system look like purely resistive load in that case, right? So if there's a voltage drop due to that inductance, I can put a capacitance in there to counteract the effect of that voltage drop, sort of thing. And that's another way I can control voltage around the power system in AC circuits. Yes, ma'am. Oh, we would love to do that. The utility only, if the voltage and current are in the same phase, then it looks like I only have resistors in the system, right? The utility, the power, the kahrama only any utility only charges consumers for the real power. Real power is what is dissipated in the resistor. The guy is doing this on the bicycle, and the guy is doing the other side on the bicycle. This is what we call a reactive power. The analogy for a reactive power. It's something that I have to have. Otherwise, everybody will fall down, on the bicycle analogy. It's something I need to have in the system because of the physics. So a transformer is something we need in the power system, right? For a transformer to operate, I need to have reactive power because there's a magnetic field set up to link. Remember, with transformer, I don't know if you've been exposed to a transformer before in physics, maybe, but the transformer is basically a core with two windings in single phase transformer. In the simplest form, it's a windings here and windings here wound in a core. If time varying flux moves around this core, then the voltage generated across these windings is equal to n d phi by dt. It's the rate of change of flux that is flowing in this core multiplied by the number of turns. So this generates a voltage. So I put a voltage here, I supply the transformer with the input from the generator. This pushes current. This is sinusoidal, so the current flowing through is sinusoidal. It goes through this winding. Right hand rule generates a flux with a certain polarity that flows in the core. This is a time varying voltage, hence a time varying current, hence a time varying flux that's flowing in the core. Links both primary and secondary. So theoretically speaking, if the number of turns here equals number of turns here, then this voltage generated across these windings is the same as the voltage generated across these windings. Right? So this idea of flux flowing in the core is something I have to represent from an electrical circuit perspective. I have to, at the end of the day, I need to draw my power system as an electrical circuit. I represent your fluid system, I'm drawing it as an electrical circuit. My electrical power system, I'm drawing it as an electrical circuit. My mechanical system, I represent it as an electrical circuit for me to solve and see what's happening. So I come up with these analogies. The analogy for flux that's flowing in a system and required to generate this transformer action, the analogy for that is an inductor. I represent my transformer in a power system at the end of the day as an inductor. That's the way that I will represent the transformer. I have to find an analogy, right? So what's my transformer doing? It is taking the voltage that you're applying, storing it in the form of a magnetic field that is linking both primary and secondary. Right? And then in the positive half cycle it does that, as well as in the negative half cycle it does it. Right? So I'm storing this energy, storing this flux in the air gap in a positive waveform, then negative, positive, negative, positive, negative. And that complies with what I said before about inductors and capacitors. You cannot keep adding flux, you cannot keep adding current in an inductor and hence storing more energy. There's a limit to how much energy you can store or how much flux you can keep or maintain around an inductor, right? And that is limited by the physics. So you cannot push more flux in this core. This core is a magnetic material. There's a limit to how many flux lines you can push in this core before it saturates. If it saturates, it becomes like air. You try to push more flux through it, and how do you generate flux? From current, right? It means like you're trying to push more current, but it does not take. It's not resulting in flux anymore. So it's like basically burning current. You're pushing more current. You're increasing the voltage. Current is increasing. You're thinking that flux increases, but it doesn't, because you have a limited space. The flux density of the core has a certain limit, right? So we represent these transformers as an inductor because they utilize flux flowing in the air gap in the positive cycle and the negative half cycle to link the two terminals of the transformer together. So what was the reason? Why were we talking about this? We're talking about So these capacitors and inductors will exist. So these inductors will exist in the power system whether I like it or not. For example, anytime I have a transformer, I will put an inductor in there in the equivalent circuit. Anytime I have a motor, an electrical motor is exactly the same way. I have an electrical motor, I supply it with electrical power. How does the rotor spin? The rotor spins because it sees this electrical current on the stator on one side. This electrical current creates this rotating magnetic field. It's creating a magnetic field in the air gap. This magnetic field in the air gap, the rotor sees that magnetic field in the air gap, like a magnet, north and south. The rotor is like one magnet, and the stator is like one magnet. If you move them together, they will move. If one is north, one is south, they will move together. You want this to happen. So how are you creating these magnets? Electromagnetically. You're creating the magnet on the stator side by supplying the current on the stator. How are you creating the magnet on the rotor side? Well, what happens is, because of the stator side creating this magnetic field that is rotating, three-phase voltages that are changing with time, what happens is this rotating magnetic field exists in the air gap. Right? So you see a rotating magnetic field in the air gap, and the rotor is basically a set of windings, piece of wire. Pieces of wire see time varying magnetic field, current will flow through them. Current will flow through them. So there will be a force generated and a voltage. If you create them in a turn configuration, a voltage will exist. Close the turn, and current will flow. Current will flow, force will be generated, right? And then you have motoring action happening, right? So this magnetic field was required. Magnetic field that made the rotor see the stator. The rotor doesn't see the stator. They do not see each other unless this magnetic field comes into play. The magnetic field exists, then the rotor sees the stator and they work together, right? If the magnetic field is not generated in the gap, then the rotor will not see the stator, right? So I had to have the magnetic field. The magnetic field is required to transfer the energy. It is required. I mean, it's something that we cannot live without. And this magnetic field that is required to transfer the energy, I represent as an inductor. So all of these motors that we have in the power system, all of these cables, anytime you see a piece of wire, cable with a wire, piece of cable with current flowing through it. Current flowing through a piece of cable is nothing but will generate a magnetic field around it. This magnetic field is stored energy, right? Which we represent as an inductor. So all these cables in the power system we represent as inductors. The transformers represent as inductors. The electrical motors we represent as inductors. So our power system is typically looking like a big inductance, maybe in a small resistance, because the resistance is big, then I'm burning power uselessly, right? So it's typically an RL circuit. So we have these capacitors around the power system to help us control the voltage or cancel the effect of these inductors, basically. Right? So all of this will appear in anytime we talk about sinusoidal steady state analysis, sinusoidal analysis. I think we should go to the slides, otherwise I'll spend hours and hours talking about different things. And you may like that, because then I don't talk about the core of the material. And then you make yourself, yes, good, interesting stuff. It is the stuff on the exam. No, great, he spent the whole class doing this. Anyway, so back to the slides so we can refocus now. So before, when we talked about our RC circuits, for example, forget about the fact that we have a sinusoidal source here. If we don't have a sinusoidal source at all, if we don't have a source at all, what would happen to this capacitor if the capacitor was originally charged to some value? Capacitor voltage would do what? Or this is the capacitor current. Capacitor voltage would have some value. It was originally charged to some initial condition. You connect it across a resistor. What's going to happen? The current or the charge that was stored in the capacitor will flow in this RC circuit, and after a certain number of time constant, decay to zero. Right? It has a certain voltage, then the voltage will drop to zero. Right? And that's what you see here. Right? So this is the current. This is the current waveform. This is the current waveform due to the fact that you had initial charge on the capacitor, and you connected that across an RC, and you connected a resistor across that capacitor, for example. Now let's say I added a sinusoidal source. If I add a sinusoidal source, what's going to happen to the circuit? If I have a voltage source, I will take that voltage source is connected across some RC components, right? These RC components have certain values. I'm not talking about steady state solution here. I'm talking about AC sinusoidal steady state solution, right? So if this was a DC source, what would be the value of current flowing in the circuit? It would be the value of the source, let's say 2 in this case, not 2 sine omega t. It would be 2 divided by what? Divided by 5 kilo ohms. right? So 2 divided by 5 is what? 0.4, 0.4 something, right? So it's 0.4 ohms. 0.4, this is kilo ohms, so this would be 0.4 microamps, I guess. No, this 2 divided by 5 kilo ohms would be milliamps, 4.4 milliamps, 0.4 milliamps, 0.4 milliamps. Now I don't have a resistor only, I have a capacitor. I'm not talking about steady state solution, right? So I expect to see what? What do I expect to see? I expect to see the contribution of the initial charge happening, right? I have a capacitor that's initially charged and a source and a resistor, and I close the switch at a certain time. I expect to see what? I expect to see the effect of the initial charge in the capacitor doing something. What would the initial charge in the capacitor do in a circuit without the source? It would discharge through this resistor. Also, if I have a source and this capacitor is not charged, what would I expect to see? I would expect to see this source charging this capacitor if it's positive, discharging this capacitor if it's negative, right? If it's negative, I will push current in the opposite direction, right? So what's going to happen is this source will have an effect on the circuit, as well as the initial charge will have an effect on the circuit. The effect of the source is what we discussed, right? If IC is equal to C dVc by dt, if the source is a sinusoidal voltage, then the current will be sinusoidal as well, but phase shifted with respect to the voltage. Phase shifted by 90 degrees, if it was only a pure capacitor. But if it's a capacitor and a resistor, we say it's going to be, instead of 0 in phase or advanced by 90 degrees, to be somewhere in the middle. So we expect, if this is a sine wave, 2 sine 200t. So the voltage was a sine wave that started at 0. The voltage was a sine wave that started at 0. Just stop, background. The voltage was a sine wave, 2 sine 200t. So the voltage was a sine wave that started at 0. And this is my attempt to draw this, right? So this was the voltage that you applied. This is 200 sine t, right? If it was a pure capacitive circuit, IC, this is current that I'm drawing, equals C dV by dt, which V is the voltage across the capacitor. Some of the voltage is across the capacitor, some of the voltage is across the resistor here, right? So, but for simplicity, let's assume it's across all the voltage across the capacitor. If it's all the voltage across the capacitor, then IC is the differentiation of that. Differentiation of a sine is a cosine. So you'd expect the current to lead by 90 degrees. So I would expect for this specific voltage, if I had a pure capacitive circuit, that the current would look like this. Right? This is at 1, maximum magnitude. But I don't have a pure capacitive circuit. It's not only a capacitor, it's an R and a C. So I expect the current, which is the blue waveform, to be leading the black waveform, which is the voltage is starting at 0, by some angle. This some angle, and it is leading it, right? So it is leading it. The zero crossing of this waveform is somewhere here. So it's leading the zero crossing of this sine wave by some angle. It's going to be less than 90 degrees because it's not a pure capacitor, right? So that's the effect of the sinusoidal source. How about the effect of the initial charge in the capacitor? The initial charge in the capacitor, if it exists in this circuit, let's say without the sine wave, because originally we considered the effect of the sine wave source on the RNC without the initial charge. Now let's consider the effect of the initial charge in the capacitor without this source. The effect of that will be that this capacitor that was originally charged, will discharge through the closed loop into this resistor, right? So note that the direction of the current is opposite, right? So one way is charging, the other way is discharging, right? So what we expect to see is that this capacitor's voltage will decay, and the current flowing through it will also decay. And that is the current flowing through this capacitor. So the sum of these two responses is what the actual circuit will do. And that's what we see here. What we see here is that, initially, fine, instead of the effect of the sine wave, the sinusoidal source, producing some sine wave that is phase shifted with respect to the voltage only with a specific magnitude that is always constant, initially due to the transient response, the first half cycle has a lower magnitude because of this negative portion here. Right? So here they added the forced response. You remember the last transient response we had the forced response and natural response. So and here it's the same. We have a forced response due to having a source. The source is forcing the circuit to behave in a certain way. The circuit also has a natural response. The natural response of the circuit is due to the fact that these components, capacitor and inductor, may have some initial charge or voltage across them. Right? So there's a natural response due to these components being charged, and a forced response due to the fact that you have an external source. It's forcing its response. Right? And the transient response is typically a few time constant. Right? So I typically don't care about it. So in this chapter I will not care about it. I will only talk about steady state sinusoidal analysis. So I only talk about what's happening later. What's the initial charge in the capacitor, forget it. Finish. We dealt with that in the transient response. Right? In the previous chapter. Now I want to look at circuits with sustained sinusoidal excitation. So everybody understands the difference between last chapter and this chapter? Okay. So for us to sort of talk about this, we sort of need to review a few things about sinusoidal waveforms and phasors. So if you have a sinusoidal signal expressed as V maximum cosine omega t plus a certain angle theta, the way we would draw this is as follows, right? This is a waveform with a peak value of V max, right? So this is the peak value of the sine wave. So this is V max. Can you see it? This waveform will have a peak value of V max, and if it was a cosine, it would start, its peak value would start at the 0, right? But here it's a cosine with some phase shift applied, right? So it's a positive phase shift, so it will move to the right, right? So this distance here is theta, or the corresponding time depending on the frequency of the waveform, right? So this, from this point to this point, is 360 degrees, right? So I'm going from max all the way to max, it's 360 degrees, right? So this portion here, and this, from this point to this point, it's 360 degrees in a certain period of time that depends on the frequency of the waveform, right? So this time here is called the period of the waveform, and the frequency of the waveform is 1 over the period of the waveform, right? So this time here corresponds to the angle theta that I've phase shifted the waveform with respect to the 0 start point, or the 0 time axis here. Okay, so this is generally this is a general waveform with a phase shift, cosine with a phase shift of a certain angle. And of course omega is 2 pi f, right? And f is the frequency in hertz, and omega would be the frequency in radians, right? So omega would be the frequency in hertz, and f is the frequency in hertz, and omega would be the frequency in radians. So any questions on this? And just the idea of drawing the sine wave. More on drawing sine waves and stuff, right? So for uniformity, we will sort of represent all waveforms in terms of cosines. Why? Because I want to make sure I cannot be mixing every. If I have one sine with an angle of 0, and a cosine with an angle of theta, right? I want to eventually go and draw a phasor diagram. A phasor diagram is a representation of this time domain signal on a real and imaginary plane, right? So I will take this time domain signal and represent it. How would I? What did you suggest is a good way to represent a time domain signal on an imaginary plane, a real and imaginary, a real complex plane? What tools have you studied in math that allow you to study a waveform that has a certain magnitude and phase angle? Remember rectangular representation of numbers? Have you studied complex numbers or not? Complex numbers? Complex numbers have a real part and an imaginary part, right? Should be the real, should be the imaginary axis. You want to represent a number 5 plus j2. It's a complex number. You would represent that on the real and imaginary plane this way. 1, 2, 3, 4, 5, 1, 2, right here. This is this point, 5 plus j2, right? So I can connect these two together. Does this relate anything to what you studied in chemical engineering? The connection between these two together probably does not relate to anything you've studied in chemical engineering, right? But if I'm able to, but this is basically a certain magnitude, because this is a specific distance from my origin, right? So it has a certain magnitude, and it has a certain angle with respect to my reference, which is the real axis in this case, right? So I found a way to represent a number in terms of a real or a magnitude and an angle, right? So now I can think of my, V max cosine omega t plus theta, okay? And then let's say call this theta 1, okay? And then I'll have another waveform, V max over 2 cosine omega t plus theta 2, and V max over 2 cosine omega t plus theta 1, right? These are all time domain signals, right? Time domain waveforms. These are time domain waveforms that have a peak value, a certain peak value, that here this peak value is V max. These two have the same peak value, but they are out of phase with respect to each other. They are not in phase with each other. So if you sit on the time axis and see things passing by, you will see one passing first and then the other one, whichever, depending on the number, right? So for us to represent this, we can utilize this trick here. So I can sort of say that the distance between this 0, the origin, and my final point here, which represents a number that has, this is in rectangular coordinates, and polar coordinates it will have a magnitude and some angle, right? So this point here represents a number that has a magnitude and an angle. So I can do the same thing with these time domain signals that we have. They all have numbers that represent their magnitude, and they all have numbers that represent their angles. So this is what we sort of call phasor representation. Right? I can take my time domain representation and represent it in phasor form. These two, this one and this one, are in phase. So I would draw this one as, this is 1, 2, 3. This is 1, for example. It is also 3, but 3 has a different half the magnitude. Right? So this would be waveform 3. How about waveform 2? Waveform 2 is same magnitude as this one, as this blue waveform, but with a different angle. So this would be theta 1, for example, let's say theta 2 is minus something, right? So minus something. This is theta 2, right? But same magnitude, right? So now I've taken my time domain signal and represented it as a magnitude and an angle on this real and imaginary plane. Right? So that's what's called phasor representation. For consistency, if I have also Vmax over 2 sine omega t plus theta 1, how would I do that? This is still a magnitude and an angle, but I cannot, for me to draw it in the same plane, I have to make sure that I'm drawing the same thing. So this sine is already phase shifted with respect to this cosine with 90 degrees, right? So it's best to agree that, okay, every time I see a sine, I will also convert it to a cosine, equivalent cosine. So this is also equal to Vmax over 2 cosine omega t plus theta 1. Remember, plus would take me to the right, minus would take me to the left. So I will subtract 90 degrees from it, right? So that way, I have my magnitude is this. My phase angle is now theta 1 minus 90. Right, so we will agree. We can represent everything in sines. It's okay. We represent everything in cosine. Whatever we agree to is, so in the textbook they agree. Okay, let's represent everything in cosine. And then you can do, because then we would like to do what? We'd like to add things, subtract them, divide them, multiply them. Then I want to make sure that I'm doing, I'm multiplying or adding and dividing the right same things, apples to apples, right? So is it clear, this idea of time domain to phasor? And you can now take these phases and draw the time domain signal, right? So, but what's common? What's common about all of these? Huh? Not same peak value. No, peak value here is different than peak value here. Yes, you said it. Yeah, omega is the same, right? This is just, these are all same frequency. Omega is 2 pi f. Omega is 2 pi f. These are all at the same frequency. So this phasor domain representation is for signals that are at the same frequency. So for any set of signals at the same frequency, you can draw them on the same phasor diagram. If it's a different frequency, it's not. You have to draw a different phasor diagram. You can draw a phasor diagram for any frequency, but for a specific frequency, this is a specific phasor diagram. Okay, so that's the thing that relates them. So any questions on this? We're good? And time finished? Okay. So we'll stop here.